Namaskar, my dear friends. Let us talk about Lattice Semiconductor FPGA design. So, what we are going to do in this session is we are going to talk about CrossLink-NX device, and we will be discussing about complete development of the development board which is given by Lattice Semiconductor, and complete circuit design explanation that we will do block by block so that you can have a proper path and dedication and the focus to start developing your FPGA systems. Okay, so this particular development board actually will serve you a platform or a reference where you can start designing your own circuits by yourself, whichever section is needed for you. So as you can see, this is the board evaluation board that we have already seen, and all the functions and functionalities or different section and everything is mentioned properly, that I'll discuss later on. So this is my top view, and similar to that, this is my bottom view of the evaluation board. Okay, so what we'll do is we'll try to get into the circuit part. So this is the schematic that has been given by Lattice Semiconductor, and you can see this particular this particular device actually uses 400 pin BGA package LIFCL 40 series. Okay, so you can see various, there are total 14 number of pages, and we have block diagram, USB interface, and other sections of the schematic that is there. Most important part will be like we have the configuration block, we have like power decoupling as well as power regulators and everything. Those are most important parts. And then a very beautiful application is given as camera interface, as well as we have various IOs like switches, push buttons, and LEDs. So why don't we do one thing? We'll start with one by one and let us see how it goes. Okay. So very first thing that they have mentioned is the block diagram of this particular FPGA. So like we have two camera interface D5 0, D5 1. Okay. To D5 1 is given just header so that you can connect an external, like a camera for your choice. And this is connected to D5 0. Then we have other parts of the schematic that we will explain one by one as we go through. The most important part is it has FPGA mezzanine connector, that is FMC low pin count connector, which is going to use bank 3, bank 4 and bank 5, so that you can have a proper understanding or proper utilization of your IO pins externally. All right. So let us proceed next. The very first thing that is coming up here is you have USB interface to your PC. So this is going to get connected to the laptop, and programming or something like that you can send it through the FTDI chip. So this FTDI chip is actually going to convert the output signal to JTAG signal, and this JTAG signal will be used to configure the FPGA. Similar to that, it has a interface to UART to USB, and then it has I2C to USB both. So this is how it has almost three interfaces like JTAG, UART and I2C. And similar to that, you can see this particular FTDI chip is actually very nicely designed with proper filtering and power supplies, and then decoupling capacitors, and we have regulated input, regulated output, and we have like data data storage EEPROM. So this is one EEPROM which is being used for this FTDI chip, and we have external oscillator that has been used. If you want, you can generate this 12 megahertz 12 megahertz oscillator for output purpose. So this can be used for driving some other external oscillators as well. Okay, the other thing is this is particular like ESD protection that has been used for your DP and DM, that is your data plus and data minus signal of your USB signal. This is DM and DM minus. Okay, see DM and DP. Okay, now let us move to the next part. So this was all about USB interface. Coming back to the next part, we have camera interface. So you can see we have a camera module here with a 30 pin connector. This is a very standard connector that is always used, and you have the differential clock lines that is used, clock N and clock P, and then we have data line, differential data lines, that is 0, 1, 2 and 3. So this is the camera module that is going to be used for data line as well as clock differential lines. Okay, seeing further, what we can see here is we have a requirement of several voltage levels for this particular camera module, like 2.8 volt, and then we have 1.8 volt, 1.2 volt. That all is generated later on. I'll tell you how it is generated. They are actually generated from LDOs, so that we'll discuss. There is a requirement of clock signal for this camera module, which is being generated by this particular oscillator, which is 27 megahertz. So 27 megahertz is being used as a clock signal for this camera module. And we have SDA and SCL line for I2C interface to this camera module, so that you can like share the data and everything properly. So this is how it is done. Coming back to the other decoupling capacitors for the power supply pin, you can see you have 1 microfarad, 0.1 microfarad plus this 10 microfarad, 0.1 microfarad for 1.2 volt and 1.8 volt decoupling capacitors. Very nicely they have given the like camera module termination line as well, like 100 ohm lines are given for each of the differential line. You can see like differential line 0, 1, 2 and 3. So you can see cam 0n, cam 0p, cam 0, cam 1n, cam 1p, like that it is given. So this was all about camera 0 module. Okay, cam 0 module. Actually, this particular cam 0 module is connected at this particular location of Aero FPGA. So this FPGA is U3I block. So here this is the how it is like interfaced with FPGA pins. So if you want to you want to connect your own camera module, you can directly come here and connect it to your pins. The power supply for this particular FPGA camera module is 1.8 volt, 1.0 volt or 1 volt, or this is also 1 volt with filtering and decoupling capacitor that is connected properly to D5 signal and DPLL signal, and then VCC D5 signal. So this is analog voltage D5 and this is PLL, that is your clock voltage PLL, and this is your power supply for your IOs. Okay. Now coming back to the another module of your camera module, so we have D5 1, so D5 0 is fine, then D5 1 is there here. Same way it is also powered up with 1.8 volt and 1 volt with proper filtering and decoupling capacitor, and this is going to get connected to your external header that can be used directly to connect an camera module separately. Okay, so this is the camera module connector. All right. Alright, so this was all about like camera module that we have discussed now. Now let us talk about other parts of this circuit. So as you can see, we have Raspberry Pi section. So in Raspberry Pi section, what is going to happen is bank 6 is being used to Raspberry Pi signals, and we have Raspberry Pi signal like configuration pins as well, like TDO, TDI, TCK, and then we have I2C lines, and then we have TMS. Okay, so JTAG line and I2C lines are there with this particular Raspberry Pi IO connector. So this is having 40 pin connector which can be directly interfaced through this particular FPGA as a Raspberry Pi model. Okay. Now, if this particular JTAG connector and I2C interface is actually not mounted, so they will not be used. If you want to utilize this functionality, you can mount them and you can utilize this. Okay. And this is through hole prototype area. That is nothing, like it is just kind of, if you want to utilize these through hole pins, you can try and utilize them, not a problem. Okay. Like they are connected to some power supply and ground pins, and most of the pins are actually vacant, so they can be used for various purposes that you want to use as a breadboard or something like that. That can also be done. Okay, so if you want to see this particular thing in your board, you open your board and you can see you have this particular prototype area where all these like connectors or all these holes are being used. In the top side, if you see, this is the prototype area that has been indicated. So this is how you can utilize this particular area for a prototype development or maybe a various circuit development externally for testing purpose. Now let us move to the next part. What we are going to talk about is SerDes bank. So SerDes bank is here, serializer, deserializer and everything. So you can see you have power supply for this, and then you have power supply 1.8 volt. 1.8 volt is here as well for your VCC PLL as well as VCC auxiliary voltage. And then core voltage is here 1.0 volt, that is 1 volt for VCC SD0 and SD1. Okay. Then we have RxDP and RxDN. Like this is basically nothing but your differential line of your receiver, and then differential line of your transmitter, that is TXDP and TXDN. Okay. Then you can see you have reference clock positive and reference clock negative. This is also like loop backed, and here also it is loop backed. If you want, you can loop it back and try to develop your coding according to your requirement. Okay. Then we have oscillator section. So this particular FPGA will require oscillator to like generate its clock. So 125 megahertz is being used by default. If you want to use another clock, you can use 200 megahertz clock to run this particular FPGA. But you will have to make this jumper selections. Okay. So this is how this is going to be used, as either 1.125 megahertz or 200 megahertz. Two options are given on the board. Now let us see the next part. So as you can see, just now we saw SerDes bank. So SerDes bank, we have the a stub and a resistor selection. So you can utilize this particular areas to select your reference clock positive, reference clock negative, and similar to that, you have receiver positive line, receiver negative line, and transmitter positive and transmitter negative lines. And you have this particular SMA pairs for 100 ohm differential lines. So similar to that same SerDes lines, you have reference clock positive, negative, and transmitter receiver differential lines. Coming back to the some of the IOs lines, so let us talk about some IOs. So we have switch pin. So deep switches are actually very nicely used for setting a particular or configuring a particular IO pin to 0 or 1. So basically basically what is going to happen is, this side is open and this side is closed. So once this switch gets closed, like this side, right side, what will happen is this particular pin switch 0 will be pulled low. So you can see this particular switch 0 will be pulled low, and this particular pin IO will be taking input as 0. When this particular pin is moved right side, it means it is open. It means what will happen, the ground connection is removed, and this particular switch 0 pin is actually already pulled up here with 4.7 kilo ohm from array resistors. So these are array resistors for 8 switch being used. So this will be reading as a 1. So whenever it is closed, it will be reading 1, and whenever it is open sorry, what will happen is let me see. So whenever it is closed, what will happen is, it will be closed in this direction, and this is how it is going to go to switch 0. So it will be 1, and whenever it is open, it means it will be 0. Okay. So like that, you can decide how it is opening and how it is closing. Once it is open, then okay, sorry, one when it is open, it will be 1, and when it is closed, it will be 0. Okay, because when it is closed, it will be pulled to ground. Then we have we have FMC connections here. Like you can see FPGA mezzanine connector, I2C line, and power on reset line, and then JTAG lines. And then we have some LEDs connected in this particular bank 2. So bank 2 is connected with some LEDs, LED 8, 9, 10, 11, 12. And we have a 50 ohm loop back trace for 6-inch and 10-inch for a place TP close to FPGA, he is saying you. So so you can do that as well. So this was all about oscillator and serializer, deserializer, and then we have switches, deep switches, and everything. Coming to the next part, we have push buttons. So you can see these two push buttons can be used for your general purpose utilization. So what is going to happen is, whenever this is pressed, what will happen, this particular pin will be pulled low, and this is how push button 0 will be reading as 0 input. So this particular IO PR15A will be reading 0 as input. Okay, whenever it is pressed. When it is not pressed, what is going to happen, this particular push button is actually pulled up and this pull up actually is going to give the input to this particular pin as 1. Okay, so high. So high will be when it is not pressed, and when it is pressed, it will be 0, that is low. Similar functionality will be for push button 1, and as well as we have general purpose push button 1 more is used, that can be used for general purpose as well as some wake up application and everything. Okay. Then we have transmitter receiver UART, and we have SDA lines and SCL line for I2C application. We have 12 megahertz that was generated at the FPGA chip that can be used as a clock input. Okay. And we have several LEDs that is connected. So you can see you have VCC O1 and O2 and this O2. So around 14 LEDs are used for general purpose application. All of them are green and these two are yellow LEDs. Okay. Then we have JTAG lines here. So you can see you have TCK, TMS, TDI and TDO line for JTAG configuration. So for other purpose, I mean, there are various applications or various like methods to program this particular FPGA. So you will see various TCK and I mean JTAG lines for this particular application. So all right, let us move to the next part. We have PMOD connector as well. So you can see you have three PMOD, 1, 2 and 3, and PMOD connectors can be used for various applications like connecting your external interface boards with let us say I2C application or UART application or some SPI configuration application. Okay, some temperature sensor or maybe pressure sensor, any sensors kind of thing, they are coming up in compatible to PMOD connectors. So PMOD connectors are, let's say here it is 12 pin. So in that you can see 2 pins are power pin and 2 pins are ground pin. So these two are power pin, these two are ground pin. Okay, 11 and 5. There are PMOD connectors that is coming single row, so only 6 pin will be there. Here it is 12 pin dual row connectors. Okay, and they have been interfaced to this FPGA. In this you can see PMOD 01, 02, 03. So PMOD 0, PMOD 1, PMOD 2. So total 3 PMOD connectors are used for this particular development boards. Let us move to the next part. What you can see, we have FPGA configuration. So unless you configure your FPGA, you will not know how to run your program or something like that. So for that purpose, what is going to happen is you have initialization pin, program pin and done pin. So you can see initialization LED indicator is this place. So whenever there will be an error or something, what will happen is this init pin goes low. Okay, this is pulled up because it is an open drain pin. Now whenever this goes low, it means there is an error while configuration of FPGA. So this is how it will start glowing. Okay, so this LED will light up. Similar to that, when your programming is done, what will happen is this particular done pin will go high, and this is how this will sort, like this particular transistor will get activated and this LED will glow. So whenever done pin is I mean your programming is completed successfully, this particular LED will start glowing. When it is not done, then it will be low, and this is how LED will not glow. Okay, we have program N pin. So this program N pin, if you want, you can press this particular switch to reset or something like that, or about programming something like that. Okay, then you have parallel SPI configuration header. So if you want to configure your FPGA through SPI, you can use this particular quad SPI configuration with having all the DQ0, 1, 2, 3 data lines, and we have clock pin, we have we have clock pin, we have chip select pin, and we have initialization done pin, and as well as program N pin, and we have flash selection pin as well, chip select pin as well. Then this is the 128 megabits of SPI flash. Externally it is used to store the FPGA program. Coming down, we have ADC block. So let us see the ADC block, how it is used. So as you can see here, we have 3.3 volt connector and 1.8 volt ADC reference is being generated by this particular IC. Similar to that, one more 1.8 volt reference is generated by this IC. Okay, so one is generated from 3.3 volt and one is directly taken from 1.8 volt. Okay, and this particular connectors is actually used to select which of the reference is being used. If you want to have external reference, you can connect to this reference one connector, and this is how you can sort these together to use the ADC reference. Okay, Then this particular potentiometer is used for some ADC application. So if you want to measure your ADC, you can sort this line, and then this is how you can utilize. I mean, this inbuilt ADCs. This is having this particular FPGA is having 12-bit ADC. So this 12-bit ADC can be used to measure the ADC voltage levels at different locations or something like that. Okay. So this potentiometer can be a best application to do that purpose. We have a ADC measurement connector. So you can see you have ADC P line and N line, like differential lines are there. So you can use this particular connector to do the ADC measurement of any external application circuits. Coming back to the FPGA, like mezzanine connectors. So this is FMC connector, like U9A and U9B. So these two connectors are used, and they have been connected to the bank 3, 4, and 5. So these are the signal lines that has been used to connect to the FMC connectors. And there are various voltage labels also that has been used, like here you can see we have 3.3 volt, and we have 12 volt as well. There is 12 volt as well. And then we have VCC IO pins to select the voltage labels for the connections. And as well as you have uh, JTAG interface as well, so that this particular FMC connector can be used to configure your FPGA from external device as well. Okay. Similar to that, we have various voltage labels so that all the IOs can be selected at different voltage levels. So for that purpose, this particular LDO is being used to generate that voltage level. So from 12 volt, it is being generated as like 1.5 volt, 1.8 volt, 2.5 volt, and 3.3 volt based on the jumpers that you are going to use. If you do not use any jumper, then what will happen? By default, 1.5 volt will be there at this particular location for your utilization. Okay. So there are two pins that is being used to do this particular V adjustable. And this is how all the banks FMC connections are being interfaced. Okay. This particular pin is used for cam reset, like camera module we saw. So their reset signal was there. This can be used to reset the camera module anytime. All right. Now you can see similar to the SPI configuration, you can have, as I told you already, that FMC configuration header can be used to configure the FPGA from externally. Okay. So this FPGA FMC configuration header can be used to connect to this FMC connector, TXDP and everything. And this is how it is done. Moving to the next part. So coming back to the power supply part, you can see we have various like voltage labels, like we have 1.2 volt, 1.8 volt, 2.8, 1 volt, 1.8, one more is there, 1 volt is one more there. We have 5 volt, 3.3 volt, 12 volt. So all these things, how it is available or not on my board, so that is being developed by this particular like LEDs. So this LED is glowing, it means 5 volt is available. You can see 5 volt is connected directly. So as long as my input voltage is greater than the forward drop voltage of the LED VF, which is generally, let us say, 2.2 volt or something, okay, or 2.7 volt. So in that case, this is the voltage, forward drop voltage for the LEDs. Okay. So if it is more than that, then you can directly connect the LEDs as explained just now. LED forward drive voltage. So this one can be directly generated like this, 3.3, 12 volt, and these resistors are used to limit the current. How it is done? Let us say we have voltage drop of VF, and this is your V input. Then the current that is flowing through this particular ILED is V in minus VF divided by resistance. Okay. So basically, whatever the voltage drop that is happening across the LED, divided by this resistance will ensure how much current you want it. Okay. So to design the current, you can define the resistance value accordingly. So as you can see, as my voltage level increases, the resistance also increases. Okay. So you can see 5 volt, 4.7 kilo ohm. Here it is less, so 2 kilo ohm. Here it is much higher than 15 kilo ohm, like that. Here it is 8 volts, so it is much lesser resistance. Now what happens if the voltage level is less than the VF, then it will be tough to connect like this. Okay. 1.2 volt is less than 2.2 volt, which will not be able to drive the LED directly. So in that case, we are using transistor or MOSFET to drive this, and this is how it will be driving through the main power supply, which is 3.3 volt. So this is how LED is used to indicate the power supply very nicely. You can see same way it is done here as well. Okay. Now let us get into the other parts. So we need, like camera module power supply 1.2 volt and 2.8 volt. So that is being generated by 1.8 volt, which is going to give you 1.2 volt, and then 3.3 volt, which is going to give you 2.8 volt. All right. Now, if you want, you can, like use these particular connectors to select the voltage labels of the VCC IO 0. So let us say V3 3.3 volt level. If you want, you can sort these two, or if you want 1.8 volt, then sort these two. This is how the voltage level of your bank IOs will be selected. Similar to that, you can see VCC 1, bank 1, bank 2, all are 3.3 volt voltage levels, and then 3, 4 and 5 are 1.8 volt voltage levels, and then we have 6 and 7, they are also selectable to 3.3 volt, and this one is 3.3 volt. Okay. Now since so many power supplies voltage levels are there, so you need to have some test points so that you can probe the voltage levels and try to find out what is the voltage level that is actually coming, so that you can test the board before proceeding for programming or testing and everything, right? All right, let us move to the next part. So as you can see, all the power pins are in this particular page. So you have a power supply pin VCC, VCC AUX, and VCC AUX H3, right? H3, H4, H5. So what is going to happen is VCC lines are properly connected with decoupling capacitors along with the bulk capacitor that is there. So let me make it little bigger for you to understand properly. So this is the core voltage 1.1.0, that is 1 volt. Now we have VCC AUX analog voltage, so which is 1 volt, which is being generated by LDO and then filtered, and then after that with decoupling capacitors it is coming to get connected to VCC auxiliary analog voltage. Then VCC auxiliary voltage, it is connected 1.8 volt. So you can see 1.8 volt it is connected with proper decoupling capacitor on each of the pins. So make sure each of the decoupling capacitor goes to respective one by one, like pins of the FPGA. This is the no connection pin, so this is how it is connected. So you don't have to connect to any of the pins on this particular FPGA. Now this is the respective ground pin for this particular FPGA. So VSS is there, like ground pin, and then we have VSS D5 and VSS like data lines and all these things. So all these ground pins are connected together in one of the section of your FPGA symbol. Now let us talk about the FPGA regulator. So in FPGA regulator, you can see, let us say we have 1 volt, like LDO requirement. So, so that is being generated by 1.8 volt input, and this is a very nice, a very simple, a small, LDO, which can be used without any, capacitors. So that can also be done. All right, so same 1 volt can be actually taken from the core voltage that has been generated through the switching regulator that I'll tell you later. And if you want, you can mount this particular resistance as a resistor and use this 1 volt LDO. So you don't have to use this one. Okay, so you can discard this. Okay, moving to the next part. We have 1.8 volt LDO requirement for your ADC purpose. So for that, what is being done is this particular LDO is being used for your DPHI, SerDes, ADCs, and VCC AUX for 1.8 volt application. Okay, and this is being generated from 3.3 volt that we will be generating from the switching regulator that I'll discuss you now. Same 1.8 volt can be used from the 1.8 volt that is being generated from the switching regulator by putting this particular resistor, and you don't have to use this particular LDO at that time. Okay, so this is how it is being done. Now let us see the power supply input and its protection features that is being used. So this is the jack connector that has been used to supply the main power supply input, which is going to take around 11 volt to 16 volt. So basically you give a nominal voltage of 12 volt here, and a 12-volt voltage clamping like Zener diode protection, or like a Schottky protection is given here for 12-volt application. Then a very simple like fuse is used to protect the current or limit the inrush current. A 5 ampere fast blow fuse is used for this particular input power supply, which is 12 volt. Then coming back to the main regulator. So this particular regulator is going to give us 3.3 volt output with 1.35 ampere and 5 volt output with 1.1 ampere rating. Okay. So there are two outputs in this particular switching regulator, which is going to be FB2, which will set the output, this one, to 3.3 volt. Okay. So these are the resistors that is being used to generate this particular voltage level, and you can see a particular equation is also given here from the data sheet, which is 0.8 into R2 by R1 plus 1. So R2 R1 you can consider as R155 and R160. Okay. Similar to that, we have the inductor that is being used to give you the output to 3.3 volt. Similar to that, in this left side you can see you have FB1, which is going to set the output voltage to 5 volt, and this is going to come this particular voltage level by this resistor and this resistor. And you have the inductor as well, which is going to be used at this particular location to set the output voltage to 5 volt and all these things. And proper bulk capacitor is used for these two voltage levels. Like 5 volt voltage level is using 3 numbers of 22 microfarad capacitors, and you can see 3.3 volt voltage level is being using 22 microfarad capacitors of 2 numbers. Okay. Let us see the another voltage level. So you can see you have another voltage level which will be 1.8 volt, which will be 1.8 volt, that is being generated by FB2. Same IC is being used to generate 1.8 volt voltage levels, and then you have core voltage level requirement, which is 1 volt, which is being generated by the same IC from FB1. So these two resistors, this one and this one, is being used to develop this particular 1 volt output, and these two resistors are being used to develop 1.8 volt output with 4.7 microhenry capacitors in inductors in both direction. 4.7 microhenry here as well, 4.7 microhenry here as well. Moving to the last part of this particular schematic, as we have seen, so you can see this is the power tree that is going to be used to understand how my power flow actually happens in complete board. So you can see you have 12 volt input, and you have two switching regulators. Switching regulator 1, which is going to give you 1 volt and 1.8 volt. This 1.8 volt is going to generate 1 volt LDO, as well as it is going to power up your camera, and 1.2 volt output. So these three things are being done by this 1.8 volt. Okay. Now coming back to the switching regulator 2, just now we explained you that it can give you 3.3 volt and 5 volt, and this 3.3 volt is helping you to generate 2.8 volt as well as 1.8 volt and to power up FTDI chip. Okay. Then this 5 volt is being used to power up your Raspberry Pi board. So that's how it is being done. Another part is we have FMC connector, that is FPGA mezzanine connector or mezzanine card. So in that you can see this particular 12 volt directly is coming and giving you the power supply, as well as 3.3 volt is coming from here. It is going to go at this location, and then there is one more 3 ampere LDO is being used to develop different voltage levels like 1.5, 1.8, 2.5 and 3.3 to give a adjustable voltage level input for this particular FMC connector. And this is the complete FPGA power supply connections of this particular FPGA system. You can see you have different blocks are there and different power supply that is connected to each of the banks, IOs and serializer, deserializer, then ADCs, and auxiliary connector, core voltage, all these power supply is connected very nicely. So alright guys, hope you have now a complete understanding of the development board that has been developed by Lattice Semiconductor for our utilization and understanding how to how to develop our FPGA circuit using CrossLink-NX FPGA for various applications. So whichever the circuit section is needed, for our application circuits or our projects, you can take as a reference and you can utilize them for your circuit design. And if you do have any questions or any support or any design requirement is there, you can put down your queries and questions in the comment box and we shall be able to answer you out. Thank you.